presenter received a Technical Academy Award from Jessica Alba. And let's have a big round of applause for Cohen.
So I just need to start with a quick disclaimer. I work for a company that designs and sells computer chips. I'm speaking for myself and not for them. So I want to tell a story about computer chips. And I think this is a story that's maybe not so widely known outside of the semiconductor industry, but it's actually really important to people. So computer chips are everywhere. They're in our cell phones, they're in our computers, in our laptops, in our cars, whatever. We think of them as these little black discs with these, or boxes with these pins. But the important part is this little piece of silicon, which is, has the circuitry printed on it, which is in the center. And so the way this works is you start with a disk of silicon called a wafer, and essentially a circuitry is printed on it. So normally you'll print many copies of the same bit of circuitry. This is known as a die. So this is a picture of one of these wafers after it's been printed, and then you cut it up into pieces. This printing process is called lithography. It's very similar to the way, for example, t-shirts are printed. So think of a kind of a crazy printer where you have this light source, you have something called a mask, which basically blocks the light. And where the light shines through and it hits the wafer, you bathe it in some chemical. Essentially where the light hits it, it accumulates a layer of metal. And so you alternate several different masks and different chemical baths, and you can build up these structures on the silicon. So this is, for example, a circuit, and then it's actually printed, all these little tiny wires and transistors and elements are printed on this piece of silicon. So this is an incredibly fine, these are very tiny little features. So currently, technology, we can print about 40 nanometers. So that's 250 of these features in the width of a single human hair. So think about the kind of amazing engineering that it takes to build a device that's capable of that level of detail. And it's incredibly expensive. This is a picture of a fabrication plant that costs billions of dollars just to make the building, where you've isolated it from vibrations, where you can print things at that small scale. They're done by people in lab coats using these really expensive machines. They wear lab coats and things to keep their skin cells from falling into silicon, because that would ruin everything. So Moore's Law, which is, I think, something that a lot of people have heard of, but maybe don't really know exactly what it means. Moore's Law is just the observation that over the last 40 years, the size of the features that we can print shrinks by a factor of 2 every 3 years. So basically this is saying we can print smaller and smaller things over time. And that's all Moore's Law is saying. So Moore's Law is a statement about lithography. It says we can print small things. It doesn't say computers are getting faster. But as a consequence of printing smaller and smaller things, it actually turns out through a process, we can scale these little transistors that we're printing smaller and smaller, and we can run them faster. And it turns out that every time you have the size of the feature, you can get a computer chip that's 8 times more powerful, but doesn't use any more energy. So this is a really kind of amazing fact. The problem is that we've hit a limit where we can no longer scale these transistors down. And so because of that, we can still print them smaller and smaller, and they run 8 times faster, but now they use 4 times the power. So every generation now, if nothing were to change, our computers would use 4 times as much energy. And the problem is that energy is heat. So this is just extrapolating to 2030. Your computer chip would be as hot as the core of a nuclear reactor. So clearly this is impossible. And this is what's known in the semiconductor industry as the power wall. So Moore's Law is alive and well. We can print smaller and smaller things. That's actually going strong. It's amazing engineering. But that doesn't matter if you can't turn the chip on without burning down your house. Right? So the semiconductor industry is actually at a crisis right now. That we're kind of reaching this critical point where we're going to have to figure out how we're going to get around this fundamental limitation that we're having. And so I just want to mention a couple possible features. So the first is maybe the most kind of obvious, which is we can design more efficient circuitry. And so there's lots of smart people that get PhDs in things like low power circuitry. And so maybe this can push that wall out by another 10 years. Probably can't push it out that much more than that though. So who knows how far we can really go with this. The other option is to say, well, we don't really care. We'll just build a nuclear power plant. We'll build giant server farms, put them next to the nuclear power plant, and they'll just get really hot, but I don't have to see that heat. And the real question, how many nuclear power plants are you willing to build so that the internet is cool? There's sort of more engineering approaches. It turns out if you stack these things into these three-dimensional structures, they can be more efficient. There's some issues where it sort of traps the heat. But perhaps the most intriguing idea is to look to biology. So in cells where this is something called a thylakoid lumen, which is a single nanometer wide structure where photosynthesis happens. So this is 1/40th the size of the current feature. And so plants don't catch on fire, they don't explode with heat. So it is possible, perhaps, that we can build these very complicated devices at these tiny scales by looking at nature. Thank you.